Okay, so today, I know we already covered the kinematic stuff and all of these little things. In some ways, that's kind of a recap of um, our old motion stuff and then just being able to throw this extra little component in. Now we're really diving into a totally new or nearly totally new subject, which is going to be torque. So as you can imagine, we talked about rotational kinematics and how rotational displacement translates to distance, rotational velocity translates to, tangential velocity. There's an analog for a lot of these different things. And one of the trickier ones for us to introduce is this idea of torque, which is essentially the rotational analog to a force. Okay, so we can say, right, a force or a net force, right? Let's say net forces produce acceleration. Okay, a net torque produces angular acceleration.
And what is the symbol for torque?
The symbol for torque will be tau, basically a pie that lost one of its legs. Okay, so if I did, typically, yeah, it'll kind of look something like that. Maybe something that's a little bit, yeah, that's a little bit better of a representation of what torque is. And right now, because we've got so much to build up to, we're not going to look at torque in terms of, normally say F net equals ma, torque net equals, well, we got to go a little bit further before we reach that point. But what we can say is the torque is equal to F R sine theta. Now that's the equation, but we don't, it's not really good enough for us to really um, just stick with that because it's kind of like work, right? It has some similarities to the work equation, but we'll see kind of how that plays itself out.
And what is theta?
Okay, so that's exactly what we're going to try and line up here. Now let's say that we have, um, let's just say that we have like a little nut, right? Little hex nut, and I got my little wrench over here, right? A torque would be useful for producing a rotation around this point, right? Anytime we talk about the rotation of an object, there has to be a center of that rotation. So as you can imagine, if I have this little wrench and I'm applying a rotating force, the reason why we haven't had to deal with this before is because normally we've assumed that all of our forces were being applied directly in line with our center of rotation. So for example, if you've got like a pen or a ruler or something and you kind of, or maybe a calculator, and you push it, right? If I push it directly in line with the center, it will just move linearly, right? But if I push it in a way that is not aligned with the center, I'm going to get a rotation. So we haven't had to deal with that because we've been assuming that all of our forces were lined up really with the center of our rotation. But as you can imagine, if I apply a force, right, out here, I am going to be applying a torque that's going to produce a rotation of this wrench. All right. Now there might be some also translational motion that goes along with that, but right now we just want to be able to define the torque. And if you've ever used a wrench, you probably also realize that one way to get more rotating force out of that wrench is to have a longer handle or apply your force further as far out as you can. So we can talk about the torque in its relationship between the force and r, which specifically when we talk about r, it's not the radius, okay? We use r. It's not specifically it's a radius. R is specifically the distance from the center of rotation. Okay? Now, if I wanted to kind of simplify my equation, but not have it be as complete, I could really say, well, if my force is perpendicular to the distance that I've measured through r, then I can just multiply it. I can say that torque is equal to the perpendicular component of my force multiplied by the distance from the radius as I've measured it, okay? Or my center of rotation as I've measured it. So in this case, for this wrench, I would really be able to calculate for this circumstance, torque is equal to Fr, right? Because they're perpendicular. When they're perpendicular to each other, my force will just be it'll just be the product. Where we get a little bit more issue though is what if I took that same wrench? I'm not going to draw the whole thing out again, but what happens if I don't know, for some reason I decided to tie a string to it and I'm pulling this string at an angle. Well, now that I've pulled this at an angle, I would have to think about the components of the force that are actually acting perpendicular, right? So if here's F, I can't just use F and R anymore, okay? Because they're not perpendicular. I'd have to use the component of force that was perpendicular. So now we can kind of see how if this angle that I made here between my force and my radius, if this was theta, can we see that, oh, the vertical component of my force, F perpendicular is going to be F sine theta.
But you can just, wait, I mean, you can also use cosine the other angle.
Yes, but for this equation, it makes more sense to use the sine because what this theta really is the angle between F and R. You could use cosine, but it would have to be like really, you know, it makes sense to use the angle that's related to the other two quantities in the equation. Okay? And so we don't want to get confused with just using any angle. I really need to think about those two things. But that is, you know, really what I want us to focus on. One is just making sure that we understand how to define the and calculate the torque acting on an object. And specifically, you know, so we can do all sorts of things with this, and I think that calculation-wise, it's not going to be terribly difficult. One thing we do want to think about though is how gravity, right? If I hold my pen and I hold it on one end and I let, you know, I loosen my grip and I see gravity can produce a rotation in something. We haven't really paid attention to that before, so we are going to really you know, make sure that we understand this part. So are we all good on this front pretty much? Okay. So when it comes to gravity and torque, let's say that I have a let's say that I just have a board or something, right, fixed to a wall. And I know that gravity is going to produce, right? So again, I can kind of see here. Here is my center of rotation. We can call that our COR. Center of rotation is right here. So this is not balanced, right? It's going to be free to rotate. How can I think about the force of gravity that's acting on this? Now, we can do this in a calculus-y kind of way. or we can do it in a, hey, let's just think about it kind of way. The calculus-y kind of way is to say, what would I do to try and think about the torque exerted by gravity? Well, in calculus, I'd say, hey, how about I divide this thing up into an infinite number of pieces, right? And I calculate the torque that is exerted by gravity on each one of these little pieces, right? And I add all of those up.
It's an integral.
Yeah, I can do that. But would it not, I mean, it's not going to be too surprising that in this case, right, if for, now again, for this particular case, right, I've got my center of rotation all the way on one end. Would it be surprising at all if I said, for this case, again, the torque due to gravity is equal to mg times L over 2.
What's L?
The length of this plank.
Does it matter where the center of mass?
Where it's uniform. A uniform plank. So the center of mass will be the center of the plank, right? Which actually is a good question to ask, Christopher. It's really times wherever the center of mass is, right? Or specifically the center of gravity, but it's essentially the same thing as the center of mass. All right. Basically, the torque is always the torque due to gravity. We can just approximate it as being applied where the center of mass is. Okay? If I have multiple masses, I could really just calculate them separately. But the force of gravity is going to act mg times L over 2, because where the gravity is going to be applied is at, we just take the average location that gravity will be applied here at the middle of the object. Okay. Now, we do not, as non-calculus physics students, we are never going to have to deal with some sort of equation for a non-uniform substance or thing. It really would just be possibly you'd have to deal with, oh, the center of mass is actually here. Okay, that's not a big deal. Which is also why we can balance things, right? Because if we balance things, right, if I took this plank and I just set it here, right, if this plank has mass, then I can, if this plank has mass, I can see, oh, the center of gravity is actually right where my support force is. And so there, it's going to be balanced, right? The net amount of torque would be 0 because gravity's applying 0 torque. And this object is applying 0 torque. Are we okay with that? All right. So when we are trying to come up with our conventions for torque, it's very similar to our convention for our angles in that they do have a vector type of direction that are associated with them. Now, how do we measure our angles? Right? If I've got my angle measure, which direction is the positive angular displacement? Up? Up?
No.
Oh, up doesn't really help because we're talking about a rotation. How do we describe rotation?
Start from 0 degrees up to 90.
All right, what's a better way to talk about this kind of rotation?
Oh, counterclockwise.
Counterclockwise rotation is positive, right? Clockwise rotation is negative. So we are talking about a vector, but it's kind of an angular vector, and it doesn't really work to say up, down, left, right, because it's rotation. As part of its definition, the direction is always changing. But we can say the counterclockwise rotation is positive. Okay? So far, so good? Now, I'm going to give us one example where we've got a lot to do and kind of tie this back in, and that is to what we've done before, and that is to talk about equilibrium. Okay? Now, we said equilibrium, right? We kind of defined equilibrium as when our acceleration is equal to 0, right? Which means the sum of our forces is equal to 0. That's actually what we started this whole year with, the idea of equilibrium and just kind of looking at how forces have to interact in order to to keep an object in equilibrium. Now, if we're talking about adding rotation in here, sometimes we can be at different stages of equilibrium. We could have rotational equilibrium, which we've been dealing with this whole time, translational equilibrium, which is what's really being described here, or static equilibrium, which means not only is my translational acceleration 0, my rotational acceleration is 0, which means that the sum of my torques is also equal to 0. Now, dealing with static equilibrium is in some ways a lot simpler because we're not adding in angular velocity and you know, all these other components of motion. But the one thing that does make static equilibrium tricky or easy to solve is that when you're in static equilibrium, you're not rotating. So there's no center of rotate, you know, you can either say there's no center of rotation, or any place could be a center of rotation that you're not rotating about. Is that an absolutely absurd thing to say? So let's just look at an example, a really, really simple example, okay? And that example would be, and you have some in your text that you're going to look at that are going to kind of go over the same thing, and that is to say, um, let us take a let's take a board and actually let's just say that this board has no mass. That'll make it easier. All right. And let's say that we're trying to actually, let's just do one of these. So let's say we've got an unbalanced seesaw. Okay. Let's say this is 2 meters and this is 1.5 meters. If I've got a 20-kilogram child on this end, balanced, right? We're in static equilibrium by a other child on the other end. What is their mass going to be? Just as a reminder, we're just going to say we're ignoring the mass of this plank for now. So we can only just talk about two things, okay? And how they're affecting the rotation of this board. So we can solve this a number of different ways, but a lot of times it's easy to say, hey, I don't want to have to worry about the rotation that this is going to introduce, right? I don't want to pick my center of rotation to be the middle of the board because now I have to think about what this upward torque is going to be. But wherever the distance is 0, right, then there's no torque. So if I choose this to be my center of rotation, can we see that this support is not going to provide any torque? Because the distance is 0, right? It applies an upward force, but the distance, this is also my center of rotation, so that R is going to be 0, right? Torque is equal to FR sine theta. So R is 0 for this force. On the other hand, for this person applying this force, they're going to provide a downward force. And we can also say, what is the nature of the torque that they're introduced? Is that a clockwise or counterclockwise torque from this person on the right? Yeah, it's a clockwise torque. And then this person here is providing, is providing a counterclockwise torque, right? They're applying, they're both providing a downward force, but because they're on different sides of the center of rotation, they're providing opposite types of torque. So let's just look at this. So we know that we're in stationary static equilibrium. So let's just start to look at how we would balance out our torques. So in this case,
Well, we have gravity as well. Because gravity is not going to be acting the same on both sides.
we are ignoring the mass of this plank for now. If we did want to introduce it, we'd have to add in an extra torque due to gravity on the plank. But really, the forces of these people is due to the force of gravity on those people, right? So the downward force that they're supplying is really just the same as the force of gravity that's acting on them, right?
But not on the plank. If the plank has that.
Yeah, we're ignoring any force of gravity on the plank. We're just saying, hey, gravity's pulling on them, the plank is pushing up on them. That means that they are pushing down on the plank, right? So in this case, if I want to say, oh, hey, I've got my sum of my torques has to be 0. So that means, well, isn't this force going to be 200 newtons, right? So 200 newtons times 2 meters is equal to whatever mg is times 1.5 meters, right? Oh, I guess I jumped ahead. I didn't say this minus this equals 0 and then get here, but that's what we were going to get, right? So I can divide by 1.5, divide by g, right? So I end up with, that can't be right. Oh, yes. There we go. No.
Isn't the length of, isn't half the length of the board gonna be like 1.75?
Well, we're talking about, remember for R, we're talking about the distance from our center of rotation, right? So this force is being applied in a perpendicular direction, 2 meters from the center of rotation. This force is being applied 1.5 meters from the center of rotation, right?
Oh, so we're just measuring the right side.
Well, we're solving for it because we know the torque that's being applied on the left side, right?
Oh, okay. Never mind. Thanks.
So we should get to some point where we say, oh, this person, right, on the shorter side has to apply a greater force because they have a shorter distance. That means they must have a larger mass.
More mass.
Yeah, should be about 26.6 kilograms.
I'm gonna see that's 400 divided by 150.
Yeah. Yeah, I don't know why does that not work? 400 divided by 150. Why does 400 divided by 150 not work? But 400 divided by 1.5 divided by 10 give us 26.
What are you talking about? It's 26 points.
Yeah, but if you do 400 divided by 150, it's not 26.6.
No, 15 isn't 150.
Oh, sorry, it's 15. Okay, that's yeah. I'm okay. Okay.
Um,
All right, so that makes sense, right? All right, so we know those two forces, 200 newtons, 260 newtons. And then here's the other thing that we need to be able to do with static equilibrium. We know that my torques are balanced, but we also know that my forces need to be balanced. So what is the upward force supplied by the support? Well, I go back to my sum of forces have to be 0, and I see, oh, my upward force, all right, well, let's call that support, minus 200 newtons minus 260, because those are both downward forces, has to be equal to 0. Oh, the support force has to be 460 newtons. Does that also make sense? When I look at balancing torques, I have to do clockwise and counterclockwise. When I have to balance forces, I do what I did before. I go up and down and right and left. We're okay with that?
What does that first half say next to it?
Where? Support? This little, yeah, this upward force right here.
Upward force minus the down forces equals 0.
Yeah.
I agree.
Okay, excellent. All right, so that's basically what you're going to look at for your homework questions. It takes a little bit of practice, and you're actually going to just do these out of the textbook because you really do need to do a lot of drawing and diagramming to get these right. I'm afraid that if we did this WebAssign style, there'd be no drawing or diagramming. It would just be button mashing, and button mashing is not how we get where we want to get. Okay, so let's go start working on our looking at some of our homework questions and see how that goes.